So we're looking to where dy dx is equal to 0. So 0 equals x plus y minus 1 all over y minus x. Now, normally I would say that the only thing this requires to be equal to 0 is that the numerator is equal to 0. And that's what I've always read and always heard.
Okay.
The question, no, okay, no, I guess that's right, yeah. I was thinking if both the numerator and the denominator are equal to 0, then would that be equal to 0? In other words, when we have 0 divided by 0, that isn't always equal to 0, as we know from calculus. We know that sometimes that's equal to a number, and it's not 0. But, ignoring that for the moment,
I didn't realize it was ever equal to a number.
well,
I guess I thought it was vertically infinite or something, like it's an asymptote or something like that, maybe, or something. Or no, I guess that's not. That's, yeah, no, I don't know.
1 minus cosine x over x.
Okay, so
If x is 0, you have 0 over 0.
Yeah.
But this, in fact, is equal to 1. If we do the limit of this expression as x goes to 0, excuse me, that one's equal to 1. This is the one that's equal, excuse me, that one was equal to 0. This is what's equal to 1. Same problem. In other words, if x is 0, we have 0 over 0, right?
Yeah.
Well, here's a case where 0 over 0 would not be equal to 0. If I take the limit of this as x goes to 0, I get 0 over 0. Well, if I solve this using L'Hopital's rule, I get cosine x over 1, which is 1 over 1. So here's a case where the limit of two things, 0 that go to 0, equals 1. So that's the only reason I start thinking about it. In other words, this puzzles me. Now maybe it's the fact that we have to use limits in order to get this thing to go to 1. I'm not sure. But that puzzles me as to how come we can absolutely say that this means x plus y minus 1 has to equal 0. I guess it would, now that I think about it in reverse. In other words, they're already telling us that this quotient equals 0. So it's not like they're telling us this quotient equals 1. If this quotient were to equal to 1, then it's possible the numerator could be 0 and the denominator could be 0. But the fact that they're telling us that it's equal to 0 definitely tells me the numerator is equal to 0.
Okay.
So, if I solve this, I get y equals 1 minus x. So when y equals 1 minus x, we should have a horizontal tangent line. Well, if I plug that in to the original equation, I'm going to have a function of x and I will be able to solve for the x's that produce this horizontal tangent line. And that's what I'm going to do. So y squared becomes 1 minus x squared plus 2x equals x squared plus 2x times 1 minus x plus 1. And we can see that we now have a quadratic. Definitely going to be a quadratic. Ooh, no it isn't. Notice that, oh yes it is. Let's go ahead and expand this out. We got 1 minus 2x plus x squared plus 2x equals x squared plus 2x minus 2x squared plus 1. Now, how many x squareds do we have? They actually do cancel out. Oh, no they don't. We have minus 2x squared. So we have minus 2x squared, and then we have a minus 2x, a plus 2x, but we still have this 2x over here. And we have a 1 and a 1, so we have all that equal to 0. And I can factor out a minus 2, leaving behind, I can actually factor out a minus 2x, leaving behind x minus 2 equals 0, which means at x equals 0 or x equal 2, we have horizontal tangent lines. Let me just make sure I did everything right there. A horizontal tangent line occurs when that's equal to 0, so y equals 1 minus x. Plug that in, we get this. I must have done my math wrong. When I factored out the minus 2, it really left x minus 1. In other words, when I went from this step to this step, I made a math error. Okay, so they are correct. So x equals 0. Now, notice what they say here. So we're solving for x, okay? So x is going to equal 0 or x is going to equal 1. Well, when x equals 0, y equals 1, so there's 1 point. They want the coordinates. So 0, 1 is one place where we have a horizontal tangent. And also at x equal 1, and when x equal 1, y equals 0, so 1, 0 is the other place.
What happened?
In other words, we solved for the two values for x where we would have horizontal tangents. And that's 0 and 1. And as all they're doing is coming up with the not just the x coordinates, but the x and the y coordinates. In other words, they came up with 0, 1 was the first coordinate. And the second coordinate, where x was equal to 1, well, if x is equal to 1, y is equal to 0.
Now, to get these points, they sub these back into the original?
No, they sub them into this. In other words, where we have a horizontal tangent line, y has to be equal to 1 minus x at that point. And so when we solved for x and came up with 0, well, if we substitute 0 in for x, then y equals 1. That's the way we get that coordinate right there. We also came up with a solution of x equal 1. Well, when we plug in x equal 1 for here, y equals 0. So the other coordinate is 1, 0.
Yep, sounds good.
Now, notice the rest of what they say here, which is interesting. Check that these all satisfy that dy dx is equal to 0. In other words, they plug in both our x and y coordinates into the dy dx formula. And it's equal to 0 when we plug in the first set of coordinates, and we plug in the second set of coordinates, it's also equal to 0. Thus, the points on the curve with horizontal tangencies are indeed those 2 points. Now, down this last paragraph, for part C, always remember to double check all points you get through an algebraic solution. It's possible that during algebraic manipulation, you choose the sign of a square root or assume something was non-zero and divided by it. There are many ways to lose small pieces of vital information. Always go back and check that your answer makes sense.
Chose a sign of a square root?
Well,
what does that mean?
Well, if I had x squared equal 2, and I said x equals square root of 2, the real answer is plus or minus.
I see.
So if I forgot the plus or minus and assumed only plus, that would be a little error. And the other error they're talking about is one that I find quite interesting, actually. If we were to solve this equation by dividing both sides by x, seems natural enough, right?
Mm-hmm. Isn't it like you can't divide by, you have to check if you divide by x, because it could have been 0.
Exactly. In other words, you can't really divide both sides of an equation by a variable if that variable can possibly be 0. Because if it is 0, you're going to lose that solution. Notice that the way I did this, I came up with one solution only. Well, that's not the way to do it. You really can't divide both sides by x because you don't know if x can be 0. The way to do this is to subtract x from both sides, factor out an x. Now you get both solutions. That can be 0, that can be 0. So you get x equals 0 or x equal 1/6. So by solving it algebraically properly, you get both solutions. But that's what they mean by that second comment. There's always a way to lose small pieces. Or assumed something was non-zero and divided by it. That's what I did the first time. I assumed x was non-zero and I divided by it and I solved the problem, but I lost the 0 solution. It disappears if you divide by it because you can't divide by 0. Okay? All right. Let's look at my problem. Now, let me add a couple of caveats. I got this problem from my pre-calc IB student. she didn't have it written on paper. She was quoting it from memory. In fact, we had a session the other night. She said, I want to work on optimization tonight,
Okay.
but I don't have any problems. So I have no shortage of optimization problems, and I started going through a few optimization problems, and she said, well, I remember one that we had that was a lot more difficult than the ones you're giving me. So I said, okay, well, give it to me, and we'll have a look at it. And let me show it to you. I'm not sure she even gave it correctly to me, and that presents some problems, but not really. It actually opens up and allows us to consider how you would treat it if she gave it to me incorrectly or correctly. You have a three-dimensional cube that is 2 inches on each side. You have a flashlight that is 12 inches above the center on a string. And that flashlight, you can move it around, or let's say on a wire, so that it's stiff. Question is where is the best location for that flashlight to produce the minimum sized shadow?
You said the flashlight is just 12 inches just straight above the...
Yeah, she wasn't. I said, is it from the center of the cube? And she said yes, and then I started thinking about it, and I realized, I'll bet it's from the center of the top surface of the cube.
Yeah. And what was the question? Like
what position of the flashlight, where it's always 12 inches away, produces the minimum shadow? Now, I've done a lot of work on this. And
well, that would have to be just facing directly down, wouldn't it?
Well, that's what I told her the very first thing I said. I said, I'm not sure I know how to do this, but I'll bet you I know the answer. The answer is where the flashlight is directly above the center of the top face. In other words, the way I've drawn it. Okay. Now, let me see if I can draw you. I want to address some of the issues here. From above, if the flashlight is directly above the center of the face, then this is the shadow. Right?
Yeah.
Okay. And if I were to draw it on my bait.
Well, if it's directly above the face, there would be no shadow.
Well, no, because it's going to strike that thing at an angle. So there would still be a shadow. Imagine a flashlight of pinpoint size.
No, this thing is above, like I was thinking it was on the ground.
No,
it's not.
No, the flashlight is on a stiff wire above the center. Well, the ray from that beam
Yeah.
going to hit the edge of this thing. Let me draw it a little better here.
Yeah, I guess it kind of would. Yeah.
Well,
Makes sense.
yeah, I don't think it really depends on how far above the thing it is. So that light creates a shadow pattern that's like that. Okay? This is a 3/4 view. This is a top.
Yeah. Yeah, I see what you mean.
Okay, and if I call that point X and this point Y, then the area of the shadow is clearly equal to 2x times 2y minus the area of the cube, the surface area, which is 2 by 2, so that's 4. Or 4xy minus 4. So that's the area of the shadow when the light is directly above. With me?
Yeah.
Okay. Well, what happens if we move the light to here, where it's sitting directly above that point there? Now, we end up with no shadow on this side of the cube, because the light is sitting directly above that point, but we have a shadow that's a little bit bigger now.
What's that? I'm still trying to get the... now the area of the shadow for the... Oh, yeah, okay, minus... Okay,
in other words, the area of the shadow in the bottom sketch,
yes.
Shadows are always subtraction problems. So I'm taking the area of the outside curve minus the area of the cube. Oh, I just realized I did it wrong. Wow. This is a hard problem. I can't believe she actually has this problem. In the bottom picture, if the light is right there, there's actually going to be an inside shadow. No, but the shadow is going to look like this. Because this light is going to strike that edge of the cube.
Yeah.
Well, the shadow is inside. What am I even thinking? Shadow is inside that whole thing. Hold on. Think about this for a second. Okay, the light is only 12 inches away, so there's clearly going to be a shadow next to the cube. Yeah, this whole thing is the shadow. Okay, I got it right.
Right. When we got 2x and 2y, how do we come up with the 2?
Well, if I center this cube at the origin, this cube is 2 inches per side, then it gives 1 inch that direction, and 1 inch that direction, and 1 inch that direction, and 1 inch that direction. So the base of this cube is actually 2...
I was just thinking it'd be x times y minus 4.
No, because this is minus x over there.
But the whole outside...
right. In other words, the center of the cube is at the origin. So the base of the cube is 2x. In other words, this is 2x right here, and that's 2y right there.
Still not getting
If x is, excuse me, it's not 2x and 2y, it's 2. Remember, this is a cube of 2 inches on the side.
Yeah, the inside I get is 2 times 2, so that's the inside area. But the outside, isn't that just x times y? Because we don't know what those distances are.
Well,
Right?
hold on. If I draw the coordinate system through this thing here, this is x. So this outside rectangle has a base of 2x. In other words, it's 2x from here to here. And it's 2y from there to there. So the dimensions of that outside square are 4xy. The dimensions of the inside square are 4. So the area of the shadow is 4xy minus 4.
Okay, yeah, I'm with you.
Okay?
Okay.
All right.
Yeah.
Now, conceptually, if I put the light there over the cube, I'm not going to have any shadow here, right? Because the light's going to cover all of this space. But I'm going to have some shadow there, and I'm going to have a bigger shadow there because the angle is bigger. And I'm going to have, I think, the same shadow on the y coordinate.
Wait, this is, you did what now to the
light? I moved it 1 inch to the left.
Oh, I see. Okay.
So that it's sitting over that spot of the cube instead of the center.
It kind of looks like the center, but
No,
I see. So it's, I see. It's, I got you. It's over
over
the leftmost. Okay.
When it's over the center of the cube, you're going to have shadows on all 4 sides.
Yeah.
If it's over one side of the cube, you're not going to have any shadows on that side.
Right.
You're only going to have shadows here and here.
Okay, you're vertically above that leftmost center.
Right, right. Yeah. And if I were to draw the grid through that, now the question is what is this dimension right here? Because that will determine whether this shadow is greater or less than the first one. Okay, so let's look at the angles here. Let's look at the first situation. I believe I can figure out the exact area of the shadow. Okay, and here's how I'm going to do it. The light is 12 inches away from the center of the top face. It comes down at some angle that I'm not sure of, theta.
Okay.
And if I look at just there, well, I know that's 1 inch. Right?
Okay.
It's going from the center of the cube to the right edge.
Yeah, that's 1 inch.
Okay. So I can say the tangent of theta equals 1/12, which makes theta equal the inverse tangent. Let me make sure my mode is in degrees. It is. So I want the inverse tangent of 1 divided by 12, 4.76 degrees. So now, not sure I know much, but I know that this is 4.76 degrees. The angle at which that light is going to hit that edge. Okay, so where's that point? Well, if I extend this triangle all the way to the bottom, to figure out where the shadow is, well, I know this distance is 2 inches. And this distance I'm going to call x. In other words, this point right here is x. So I can say the tangent of 4.76 degrees is equal to x divided by 14. Let's come up with a number here. So I want that answer times 14.
How do I get the way? Got a little bit.
Okay. Where
14. How do we get 14 in there?
Well, we figured out this triangle here, the top triangle, because I knew this distance was 1. I knew this distance was 12.
Oh, the 14 is 12.
That dictates that theta. That theta is 4.76 degrees. Okay? Well, if you extend this triangle all the way to the bottom of the cube to figure out where the shadow is going to go to, in other words, what's this point right there on the lower right, then I'm looking at that triangle. And the angle doesn't change. The angle is exactly the same, theta. It's just a question of how far out it goes when I increase the depth by 2 inches.
Okay.
Okay?
Okay.
Yeah, so if I take tangent of 4.76 degrees times 14, I get x. Well, I didn't quite do that right. Tangent of 4.76 times 14. Yeah, I get 1.165. So this measurement right here is 1.165. Or down here, the x-coordinate is 1.165 on the lower right. Okay. Because it's a cube, and because I'm directly over the center of the cube, then I also know that this point here is the same y-coordinate, 1.165, comma 1.165.
Okay.
In other words, this same angle methodology is going to produce the y-coordinate also of the shadow. Remember, at this point, we're only looking at the shadow that's going to be produced when this light is directly over the center of the cube.
Directly over here. Okay.
Okay. So it's 4 times that, minus 4. Let me come up with that number. It's this number squared. That's x times y times 4 minus 4. So the area of my shadow is 1.43. The area of the centered shadow is 1.43 rounded off. That's 4xy minus 4. Okay? And that's what I suspect is the smallest. Now, here's where the problem comes in.
What was the answer to that area?
Well, the area of that, which I don't really know, is the minimum area, but it's 1.43.
Okay.
Okay, that's the total size of this shadow minus the surface area of the cube, since obviously there's no shadow on the cube. In other words, the only shadow is the shadow of this outside. Okay? Now, I could work through, in other words, if my life depended on coming up with an answer for this, the next thing I would do is, if you look down here on the lower right where my cursor is, I would figure out what the shadow is when the light is on that, above that corner, and I would figure out what the shadow is when the light is above that point there.
Okay.
Obviously, whatever the shadow is above the corners is the same shadow size on all three corners, all four corners, because of symmetry. And whatever the shadow is at the midpoint of each side is going to be the same as whatever the shadow would be here, here, and here.
Okay.
So if my life depended on it, I would calculate the shadow in the very middle, at one corner, and at one midpoint. And whatever the lowest number was, that's what I would go with. And I would actually feel fairly confident. Problem is, how do we know the perfect point is not there, or there, or there, or there? Now, the other thing I'm quite certain of is that she was not supposed to be able to answer this problem by finding the shadow at the middle and the corners and figuring out the minimum. She was supposed to answer it as an optimization problem. Okay? Now, let's just do a quick review of optimization problems. A really quick review. There's a house. Farmer wants to build a rectangular pen. 3 sides only, because he doesn't need a fourth side, because his house acts as the fourth side.
Okay.
He has fencing material. The perimeter of this thing is 2,000. What should the values of x and y be to maximize the area, to optimize the area?
Okay.
Okay. Now, the way optimization problems are done is you start out with your primary formula, which you want to optimize. Since I want to optimize the area, I'm going to list my area function. Well, at this point, my area function is a function of x and y, right? So it's that. Well, I can't maximize a function in 2 variables, at least not yet. I don't know how to do it. But at this level of calculus, we don't know how to do it. However, I can say that the perimeter, 2,000, is clearly equal to 2x plus y. I can solve for y and substitute it into the area function. So I have the area as a pure function of x is x times y, and y is equal to 2,000 minus 2x. And now my area function is a function of one variable only.
Okay.
Well, that's a beautiful thing, because now I can take the derivative of this function with respect to x. I can find out where it's equal to 0, and that tells me the perfect x.
Okay. I remember that that was the case. Why was that the case? Just because anytime you have you have the horizontal line there, it signifies a...
Let's plot this area function. If I were to graph that area function, it's clearly a quadratic, and it's clearly a quadratic that opens down.
Oh, okay.
If I'm looking for the, remember, this is the area.
Oh, I see. Yeah.
Okay? So, and this is x. So if I'm trying to find this point right there, the maximum of that function, I'm going to take the derivative of the function and find out where the slope of that tangent line is 0, which will be that point.
Okay.
So the key of optimization problems is you take your function, you take the first derivative of it, you set it equal to 0, and that's going to give you all the extrema. It's going to give you maximums or minimums. In other words, maybe I have an area function that looks like this. Okay? Well, obviously, if I take the derivative of that area function and set it equal to 0, I'm going to find that point, and I'm going to find that point. Well, I would have to evaluate which one gave the maximum. Clearly, that's the maximum area. That's more like a minimum area. Okay? So this concept of taking the first derivative of the function you're trying to optimize is big. Now, the typical optimization problem is one where the function you're trying to optimize is a function of two variables, like this, x and y. But then you have additional information that relate x and y. So you can then substitute for one of the variables, and it doesn't really matter which one. I could have solved this for x as easily as y, but as long as I make my function that I'm trying to optimize a variable of only, a function of only one variable, I'm in like Flint. Because notice now I can find a prime of x. Well, that's equal to 2,000 minus 2x. I'm going to set that equal to 0, which makes 2x equal 2,000. So I'm saying that when x is equal to 1,000, x, this is 4. Excuse me. I did my first derivative wrong. When I take my first derivative, it's 4x. So I got 4x equal 2,000, x equal 500. So when x equal 500, which makes y equal 1,000, because the perimeter has to be 2,000 in total, that is the maximum area that you can make that fence. 500 times 1,000. In other words, you can make it 50,000 square feet. No matter what other shape you use, you're not going to get that big of an area. There's only one area that creates that much space for your horses or cows or whatever you're putting in that. And that's when the length is 500 and the width is 1,000. Okay, and this is like the most basic of all basic optimization problems. It's where you have a really easy area function, you have a perimeter, so you can relate y as a function of x and solve it quite easily. Okay, now let's go back to this problem. If I want to solve this problem in that manner, as opposed to finding 4 discrete points, in other words, I check this point, I check this point, I check that point, and I'm relatively certain that one of those 3 points is going to give me the minimum. But I'm not positive. What if the minimum comes right there when the flashlight is only a ½ inch to the left? Or maybe it's a ½ inch left and a ½ inch up. Maybe that produces a smaller shadow.
I see what you mean.
All right, this is why I think this problem is so interesting, because I think this might be a hint at 2-variable calculus. And that's why I wanted to talk about it.
Okay.
First of all, there's any number of ways she could have given me the problem wrong. She wasn't reading it from a piece of paper. She was reading it, or she was giving it to me from memory.
Yeah.
So it's entirely possible that this light can only move in one direction. It can either move left or right. In other words, it can only move along the x-axis.
Oh, I see. Well, it wouldn't matter though, would it? Because it's a cube. I mean.
Yeah, I think it does. Well, I don't know how to solve it if it can move on both axes, unless you can help me figure it out. I think I can solve it if it moves on one axis only.
I see.
Because look at this picture up here. I've got it moving on one axis only. I've moved the light exactly 1 inch to the left on the x-axis. Okay. Now, if we were to look at this problem from the perpendicular viewpoint, I have a different triangle that I have to solve. Here's my cube. Here's my shadow. Well, this angle here, which we'll call delta, it's not the same as theta. And in fact, this distance right here is now 12 inches. All right.
Actually, the left side would be 12 inches still.
Now, if it's on a wire, remember, I'm not able to move its anchor point. This is a 12-inch radius, so that if I move the light there, it's 12 inches to the center of that spot, like my diagram shows.
I see, okay. Gotcha.
Well, I can still figure out my distances, though, because this is still a right angle. And I know this, I don't know what this angle is. But I know that's 1 inch there. So this angle here, delta, if not delta, but if I try to figure out this angle right here, that's that same 4.76 degrees.
Yeah, I guess, yeah, right. Because, well,
it's because this is a right angle, and the tangent of that angle is, no, it isn't that same angle. the sine of that angle is 1/12. So it's the inverse sine. That's not the angle we want anyway. We want this whole angle. The reason we do is because that angle is going to be the same as this angle here, and it's going to tell us how far x goes out, how far the shadow goes out. Well, this distance is 2. Wow. Oh, this is so hard. Hold on, I do have to draw that middle line, the anchor, because that's the only measurement I know. That's 12. And this is 1. So that allows me to calculate that angle, which is the inverse sine of 1/12. Let me get that real quick. Hold on a minute. Yeah, no, that's going to be helpful. Okay. The inverse sine of 1 divided by 12. Got to turn it on. The inverse sine of 1 divided by 12 equals 4.78 degrees. So this small angle right there is 4.78 degrees. That's going to allow me to figure out this measurement right there, y.
Which measurement where?
What I've labeled as y.
Oh, I see. Okay.
Okay. In other words, because I now know this is 1 and I know this is 4.78 degrees, I can do the tangent of 4.78 degrees is 1 over y. So y, let's go ahead and get that. Y should be the, let's see, if the tan of 4.78 equals 1 over y, then y is 1 over the tan of 4.78. So y is 1 divided by the tan of 4.78, 11.96. So this distance here is 11.96. We would expect it to be a little bit less than 12, right? I mean, 12 is the hypotenuse of that triangle, so that side has to be smaller than 12. Okay. Now I know this side. I know this side is 2, so I can figure out that whole angle. It's the inverse tangent of 2 divided by 11.96. So it's the inverse tangent of 2 divided by 11.96. That's 9.49 degrees. So this big angle is 9.49 degrees, which makes that angle 9.49 degrees. And now I should be able to figure out this length of this shadow extending from the cube. That's 2. So what have I got? I've got the tangent of 9.49 degrees equals x, we'll call it z, divided by 2. So z is 2 times the tangent of 9.49 degrees. Tangent of 9.49 divided by 2. Tangent of 9.49 is equal to x divided by 2. So x is the tangent divided by 2. I made a mistake somewhere. Hold on. Trying to find out that distance right there. I know this angle is 9.49, so I can say the tangent of 9.49 equals x divided by 2. So x is equal to 2 times this, not divided by that. Okay, let me do that again. Multiply this by 4, and I should have the right answer. 0.33. So this distance right there is 0.33. Or if I look up in this picture up here, the distance between the edge of the cube and there is 0.33. So I haven't changed anything with regards to y. This distance from there to there is still going to be 1.165, right? I haven't changed it relative to the y-axis. The only thing I've changed is the length of the shadow on the x-axis, which is now 2.33. Because remember, this is 2. It's 0.33 to there. So what's the area of my shadow here? It's 2.33 times 2.33. Ooh, that's interesting. Mine, and that's going to be the same number. It gives you the same shadow size. It's 2.33 times twice that, the length of that vertical dimension of the shadow. So it's 2.33 times 2.33 minus 4. I think that's the same number. 2.33 squared equals minus 4 equals 1.42. Is that not what I got before?
1.43.
Same number. In other words, I rounded it off. And I rounded this one off also. That rounds off to 1.43. Interesting. So moving the flashlight from above the center of the cube to the left center of the cube produces the same size shadow. Here's what I wanted to talk about, though, is all I did was test 2 discrete points. And I got the same size shadow. That doesn't tell me that maybe if I move the flashlight right there, it's a different size shadow. How can I determine it? Well, if I can make the area shadow function, which is currently a function of 2 variables, a function of 1 variable only, I can differentiate it and set it equal to 0 and solve for it. Well, here's my area function, 2x times 2y minus 4. And notice that I can make x a function of theta. So I could turn my x variable into a function of theta. And my y variable, this is, see, I'm pretty sure I could solve this if you could only move your flashlight horizontally and not relative to the y-axis also. I don't know how to, in other words, I would have a different angle. This angle theta, if I start moving this flashlight to there, now I have an angle delta. That's the angle measured from the y-axis instead of, or the x-axis as opposed to the angle measured from the y-axis. I'm in a orthogonal plane. And that's why I think that ultimately this is a calculus problem with two variables, which I'm not sure I've ever seen before. In other words, our textbook says, well, actually my textbook says calculus in a single variable. The 15-chapter textbook that you have a digital copy of, I think that actually does get the calculus of two variables. It's just we've never done it before. I cannot relate y to x. So I can't turn this area shadow function into a single variable. What I originally thought I could do was I could relate x to theta, which I clearly can. The tangent of theta equals x over 14. There's my theta right there. Theta being a measurement of how far you move the flashlight off the center. In other words, when the flashlight is dead on the center, there's no angle other than perpendicular to the middle of the cube. But when I put the flashlight over there, there's this angle here that is different than theta, and it's a measurement of how far I move the flashlight off the center of the cube. And I was thinking that I could define x as a measurement of theta, and if I could define y as a measurement of theta, then I could make my area of the shadow function strictly a measurement of theta, and I would be fine. I could take the derivative of it, measure what theta gives you the zero tangent line, the zero derivative. Problem is that theta is only measured in 2 dimensions up here. This theta, actually not even this theta, down here, this angle, in other words, when I move the flashlight off the center to the edge, it creates a different theta, creating a longer shadow on one side of the cube. But from our calculations, it looks like it's exactly double, which means the total shadow is the same because there's no shadow on the left side. There's no shadow there, but there's twice as much shadow there. But if I'm allowed to move the flashlight along the x-axis and the y-axis, then, in other words, if I drew a picture of what it would look like if the thing was not on the center and not on the edge, first of all, if I put it at the corner, the shadow is going to look like this. That might actually be the minimum shadow. I would have to figure out the angle of incidence that the light makes to figure out what that point is right there, and then calculate the distance of that shadow. But that, again, is doing it discretely. And like I said, there's not much doubt in my mind that the minimum is going to come at one of those 3 points. It's going to come either when the light is directly over the middle, or it's at the corner, or, excuse me, there would be the middle, there would be a corner, and there would be the middle of a side. And what we proved was that the shadow is the same if it's there or there. I still haven't done the math to prove what the shadow is going to be if it's there. But most importantly, I haven't considered what if it's in this area here, somewhere not at the center or at the edges. What if that produces a smaller shadow? And the only way I can do that is if I can figure out the area of the shadow as a function of one variable, and that variable has to be the position of that flashlight. The problem is the position of that flashlight is two variables. I can move it along the x-axis, but I can also move it along the y-axis. In other words, if I put the flashlight right there, I've moved it a little bit with respect to the x-axis and the y-axis. So there's no single angle that I can define x and y as. In other words, I have my area function. My area function is 2x times 2y minus 4. And I know that with some of these optimization problems, if you can turn this into theta and this into theta, that's fine. In other words, I don't have to turn y into x or x into y. I can turn both of them into a third variable. Then I will have my area function be a function of theta, and I'll be able to solve for which theta produces the minimum shadow.
Yeah, I see what you're saying. How to do that, I would not know.
I'm sitting here trying to think if there is a single variable that I can use to define that position of the flashlight. To me, that position of the flashlight, what if I draw a line like that, and this theta, I would need polar coordinates. I would not just need a theta, I would need an r. In other words, if I had this position defined in polar coordinates, some theta with respect to the horizontal, and some distance, I might be able to solve my problem. But that has to be so far beyond, that's chapter 10 stuff at best. I'm not even sure we can solve this with chapter 10. But perhaps by using a polar coordinate system to locate the flashlight, in other words, when the flashlight's dead center over the cube, it's an angle of 0 and an r of 0. When the flashlight is in this position, it's an angle of 0 and an r of 1. So if I can come up with theta and r as an answer, that is my answer. But it seems to me I would have to use polar coordinates to do that, and even that, I don't know that I know how to do it. I'm meeting with this girl again on Thursday, and she's going to have the exact problem on a piece of paper to read it for me. She did give me one other piece of information here that she knew, and that was what was the minimum size. She knew the answer, but to me that doesn't help. In other words, if her minimum answer agrees with this, well then I know what the answer is. But if her minimum answer is some number less than this, I'm back to square zero. I have no idea how to proceed on it.
Yeah, I see.
But that polar coordinate has a lot of promise, because using a polar coordinate system is a way, because the flashlight has a radius of 1 foot, in other words, it can't go any outside of that 1 foot radius, then it really can only move on the x and the y axis. It can't move on a z-axis. It can't get any closer to that cube. It is 1 foot away from that cube regardless of where it's at. So I can move it anywhere on the x-axis or the z-axis. Now, it's clear to me that there's no way the flashlight can be outside the edge of the cube. That obviously is not going to produce a minimum shadow. That's going to produce a bigger shadow on the opposite side. So I know the answer has to lie somewhere in that 2 inches by 2 inches. I don't know. I don't know if I've wasted your time for an hour or not, or whether you followed it, but I'm not sure I've made any progress on it. The last insight that may have been helpful was converting this to a polar coordinate. Allows me to move that in 2 dimensions, the flashlight. If I can only move the flashlight in 1 dimension along the x-axis, I'm pretty sure I can solve the problem. And I'm pretty sure I can solve it anywhere in between the center and the edge, because I can come up with an area equation that is a function of the amount of distance that it's been moved along the x-axis. Very easily I can come up with it as a function of 1 variable, and which means I can solve it. I suspect the answer is the same shadow regardless of where you're at on this line here. But it wouldn't surprise me terribly if there was a different spot in here that produced a smaller shadow. It actually would surprise me, because based on symmetry and the fact that circles are the most efficient objects, intuitively, I gotta think that this flashlight has to be right over the center. And in fact, I'm a little surprised that it gave me the same shadow when I put it there. It almost makes me believe that no matter where I put it above this thing, it's going to give me the same shadow.
Yeah, maybe.
But I don't even know how to analyze it when it's off the x-axis. I mean, I do know how to analyze it on a discrete mode. If you said it was at this point right here, I could calculate the shadow. But I can't figure out how to minimize the shadow, which requires coming up with an equation of the shadow, being able to differentiate it, set it equal to 0, and solve for 1 variable.
Yeah.
I don't know. I guess we might as well stop there. I think I'm just going to wait until my session with her and have her give me the complete problem, and she'll probably give me conditions that were completely more confining than this. I can't imagine that she can move this flashlight in 2 directions and they expect her to solve this. Maybe. But if so, boy, she's a junior in high school.
Seems like they're just assigning them problems they can't do.
Well, IB is like that. I have run into this with IB. Unbelievable. I mean, pre-calc IB.
What are they hoping to do?
I don't know. I don't know. To me, I don't tell parents this, but I want to, and I have told a parent this. I told a parent this once, and I said, if I had a child, I would definitely not put them in the IB program. The IB program goes out of their way to confuse. They don't go out of their way to make people understand. They go out of their way to confuse people. I've seen it time and time again. And to me, that's not, if I want to teach you how to ski, I am not going to start you on the expert slopes and say, get down the hill.
Yeah, right.
I'm going to start you on the beginning slopes, and then the medium, and then the experts. I'll work you up to it. And the IB starts them with these such ridiculously hard problems. Who knows? Maybe by the next time I talk to you, I'll know how to do this. And I'll let you know if I do.
Sure. Sounds good.
All right, Timur.
Okay, Dave. We'll talk to you next time.
Bye-bye.